20,000 Hz. Infrasound is the exact opposite. So at the lower end of our human hearing range, which is 20 Hz, all the frequencies below 20 Hz are considered infrasound. So not that many, anything less than 20, so 19 through to 1 is infrasound. Now, the first and most important thing we need to be able to do is say, right, what are some uses of infrasound? So in particular, what we're going to look at in this section is the production of infrasound waves, which are known as seismic waves during an earthquake. So earthquake waves are known as infrasound, they're seismic waves specifically, and a use of those is obviously determining where an earthquake took place, so detecting seismic or earthquake waves, determining the internal structure of the earth using those seismic waves, which is something we'll look at as well today. There are also animals that use infrasound. So again, just like ultrasound, if you want to refer to the uses as being communication between animals, you have to be specific in the animals that you choose. So for infrasound, we can use elephant communication, giraffe, or even whale communication. But to say animal communication is too general. We have to be specific in the animals that we choose. So I'd say the three main ones we want to go for are detecting earthquakes using infrasound. We can also determine the internal structure of the earth using infrasound, and animal communications such as elephants, giraffes, or whales use infrasound. There are obviously more than those for uses as well. There's some on this diagram, but main three is the most important. Moving on, we're looking specifically, so for infrasound in this chapter specifically, we're actually going to focus on the seismic waves. So we said that earthquakes, when they're created, they produce seismic waves, which are infrasound. And these seismic waves can be categorized into two separate waves. So you have P waves and S waves. Now, we need to know specifically a few different characteristics and a few things about those waves in particular. So the P waves are called P waves because they're either known as primary waves or pressure waves. Now, the primary just refers to the fact that they actually arrive first at the seismometer and the seismograph, so at an earthquake detecting station. The P waves will arrive first because they travel faster, so they're called P waves for primary, or pressure waves because they're actually a longitudinal wave. So the P waves are a longitudinal wave. So of the infrasound, the seismic waves P and S, P is the longitudinal wave. And one of the most important things for this chapter that we need to know is that P waves can travel through any material. And the reason that's so important is because it helps us determine the different structures of the earth on the inside, knowing these facts about those types of waves. So P waves are longitudinal, they can travel through any material, solid, liquid or gas, not a vacuum because it's longitudinal and it requires particles to travel. And obviously we know that longitudinal waves, the vibrations of the particles in the matter are parallel to the direction of the wave travel and the direction of the energy. Alternatively, the S waves, so the other type of seismic wave, which is known as an S wave, is known as S because it's secondary or shear. And the secondary just refers to the fact that it arrives second because they're slower than the P waves. And the shear actually refers to the fact that the particle oscillation is perpendicular to the direction of the wave, which is a transverse wave. So S waves, secondary or shear, transverse waves, not longitudinal. And finally, S waves can only travel through a solid. So, although P waves can travel through all materials, solid, liquid, and gas, S waves can actually only travel through a solid. And again, that's a really important piece of information for us to determine what the internal structure of the Earth is. Now, we're going to look at how we actually use those facts about P and S waves to determine what is inside the Earth. So we're going to start by looking at a diagram. For example, if we were to look on the inside of the Earth, if an earthquake took place at the top of the Earth, so the epicenter of the earthquake was at the very top, and we drew the paths that those seismic waves took through the Earth, so P and S waves both created at the earthquake epicenter, and they travel through the Earth, you can see on the diagram that actually they take curved paths through the Earth. Now, the reason that the waves, both P and S, curve through the inside of the Earth is because the deeper they go through the mantle, and obviously we know, or we assumed initially, that the whole Earth was made of solid. The deeper you go into the mantle, at least, the more and more dense it becomes. And because there's a density change in the material that the waves are traveling through, we know from foreseeing refraction that the waves are going to change direction. Now, because the deeper they go, the density changes constantly. They're constantly changing direction, causing them to have those smooth curves when they pass through the Earth. So it's about refraction and the density of the solid they're passing through. Now, interestingly, if we're detecting the earthquakes at the bottom of the Earth in this example, so the opposite side of the Earth from where the earthquake took place, then we'd assume if the Earth was completely solid, that both P and S waves would be detected at the opposite side, because we know P waves can travel through all materials, and we know that S waves can travel through solids. So if it was solid, all of the P and S waves would be detected at the opposite side of the Earth. And now that's not the case. So an observation that was made is that if you detect earthquake waves at the opposite side of the Earth to where the epicenter took place, no S waves actually arrive at the opposite side. So no S waves are detected, which means there's an S wave shadow zone. Now a shadow zone is just a region on the Earth where those waves aren't detected, they don't reach. And the fact that there is an S wave shadow zone at the opposite side must mean that something is stopping them from coming all the way through. And because we know they travel through solids, it must be a different material inside the Earth, such as a liquid, which is stopping the S waves. The P waves, on the other hand, they get through and they do arrive at the opposite side of the Earth, but the S waves are stopped. There's an S wave shadow zone, and therefore there must be a liquid outer core inside the Earth. So the observation for the conclusion that there is a liquid outer core is that no S waves are arriving at the opposite side of the Earth where the earthquake takes place. Because we know they travel through solids, it must be a different material, and liquid is the one that we decided makes the most sense. So there's a liquid outer core which creates that S wave shadow zone and stops those S waves. Now, it's not the only thing that actually happens because of the liquid outer core. We said that P waves can travel through all materials, solid, liquid and gas. So yes, the P waves do arrive at the bottom on the opposite side here. However, there is a P wave shadow zone on the sides here and here. Now, it doesn't make sense that there's a P wave shadow zone because P waves could travel through anything, so how can they possibly not travel to these places? Why is there a P wave shadow zone? And it's not because they can't travel through there, it's because when all the waves of P and S reach the boundary of the liquid core, we know that 4 things can happen. But because the liquid is so much different in terms of density to the solid on the outside, actually the speed of those P waves when they enter the liquid core change quite a lot. So that although they're curving the whole time through the solid, when they hit the boundary to the liquid core, they refract quite a large amount. So their refraction is very big in the liquid core, and it actually refracts away from these areas of the Earth. So the P wave shadow zone is due to the refraction at the liquid core being so much greater than the general refraction inside the Earth, and therefore it refracts away from those regions, giving you P wave shadow zones at the sides. So that's the reason for the P wave shadow zone. Now, the very, very last step and the very, very last advancement in our theory of the internal structure of the Earth came from the fact that, although we've just said there are P wave shadow zones on the sides of the Earth because they've been refracted away by the liquid boundary, a little bit later on, as technology advanced and more observations and research was made, there were very faint and small amounts of P waves detected inside the P wave shadow zone. Now, what we're saying is, well, we've just said that there's a region where no P waves can be detected because they were refracted away by the liquid core. But later on, we're saying, hang on a minute, there are small amounts of P waves arriving back inside their own shadow zone. What could possibly send some of those P waves back inside their own shadow zone? And the conclusion is that maybe something even smaller inside the liquid core is refracting them again for a second time back inside their own shadow zone. So the final conclusion that was made is that not only is there a liquid outer core inside the Earth, but there's also a solid inner core, which is smaller, inside that liquid core, which refracts the P waves back inside their own shadow zone. So there are the 3 divisions. We know the mantle. There is a crust as well, but it's less important at this stage. The mantle, which is solid, which the P and S waves both travel through. Then there's a liquid outer core, which the P waves can travel through, but they get refracted when they go through it, so they don't arrive at the sides, so you have P wave shadow zones. And the S waves, which can't travel through liquids, get stopped at the liquid core, so you have a really big S wave shadow zone at the opposite side where no S waves can arrive. And then you have a solid inner core inside the liquid core, which the P waves that are traveling through the liquid, only some of them, because it's smaller, get refracted again back inside their own shadow zone, and therefore that's why we came